This course module covers the technical fundamentals for the treatment of potable water. As mentioned earlier, the water cycle is very complex. However, if we break it down to some basic applications and measurements, it is much easier to understand. In this section, we will explore 4 of those application and measurement points, the first being the use of magnetic flow meters for flow measurement using Faraday's law. Our Aztec series of analytical measurements using the Beer-Lambert law measure a wide variety of chemical properties found in the treatment process, including iron, manganese, and aluminum. Our ability to monitor the cleanliness and color of the water using turbidity and nephelometric metering. And finally, ultrasonic and laser level detection, keying, storage, and monitoring of the level of water throughout the process.
Whilst electromagnetic flow metering is primarily used in full pipes, it also makes it suitable for partially full pipes and channels, often found in effluent applications. Electromagnetic flow metering is based on the principles of Michael Faraday's 1832 discovery. When a conductive liquid, such as water, is moved through a magnetic field, a voltage is induced in the liquid at right angles to the magnetic field. The size of the voltage is directly proportional to the volume flow rate. This induced voltage is detected by sensors known as electrodes. These electrodes transfer the voltage signal to the processing electronics, where it can be converted into a usable industrial standard signal. It's important that the flow meter tube is non-magnetic, and austenitic stainless steel is the most commonly used material. It's also essential that the flow meter tube has a lining that electrically insulates it from the liquid inside, and provides a non-reactive barrier with any corrosive liquids being measured. Distinguishing between flow-induced voltage changes, electrochemical noise, and plant-induced noise is a barrier to accurate electromagnetic flow metering. This can be especially difficult in dirty and industrial applications.
The 2 basic methods of colorimetric analysis in use today are manual and automatic or online systems. Manual methods are accurate, as samples are taken and analyzed in a laboratory using either a handheld kit or a spectrophotometer. The main drawback is the amount of time elapsed between the extraction of each sample and its subsequent analysis. It provides accurate results, but only for that moment in time. There is no way of knowing what is currently happening in the process. Automatic or online methods, on the other hand, provide analysis at regular intervals. Samples are analyzed at the point of extraction, which provides real-time indication of current process conditions, and allows immediate and continuous action to be taken to correct any problems. It uses several methods of monitoring the quality of water as it is processed. One of these methods is colorimetric. Phosphate, iron, aluminium, and manganese are detected using the Beer-Lambert law of color absorption. The rules of absorption are summarized by the Beer-Lambert law. This law states that the absorbance of UV, or visible radiation, A in our diagram, is proportional to the concentration of the absorbing compound, C, and the distance the light travels through the solution, I. This is expressed by the Beer-Lambert equation. To guarantee water quality during the final production stages, the measurement of clarity of the water is important. There is a turbidity measurement to ensure the water meets local government regulations. Required by regulations in most water facilities, uses reflective light to take measurements. There are several different light sources available, for example, white light, infrared, and laser. Better known as turbidity, nephelometric meters are used in a process to measure particle sizes. This is critical in obtaining a good quality water measurement. There are 2 methods of detecting turbidity. The first low-level detection is normally done using scattered light methods. A receiver is placed 90 degrees to a light source and will measure the scattered light from particles within the liquid. The second method is an absorption technique, where the receiver is 180 degrees from the light, and the amount of light absorbed by the particles is directly related to the particle size. Level measurement including ultrasonic, laser, and hydrostatic. These different methods are explained in the following 3 slides. Ultrasonic level measurement is the most common level measurement in the water segment. A very simple method of sending a sound signal towards a surface and then measuring the reflective time is the method behind ultrasonic flow measurement. As depicted above, a transmitter sends an ultrasonic pulse down and an echo is listened to by a simple microphone. This method is also used for measuring water flows. Ultrasonic can also be used in detecting the level in a weir, notch, or flume application. The transducer is positioned above the liquid level. With the aid of built-in linearizers, level can be accurately converted to flow. The sonic transducer can then indicate flow and totalize. This is also a very common measurement within the water segment. As with level measurement, a simple signal is sent and reflected off the water surface, indicating the level within the weir or flume, and can be easily converted into a flow measurement. This is also commonly known as open channel measurement. A second method of level detection is the use of a laser. While a little more expensive, lasers do offer a very narrow beam select measurement. A beam angle of less than 0.2 degrees is used and a simple laser emitter and receiver to measure the height of a level below the receiver. This can also be used in obtuse angles of up to 45 degrees. What you should have learned so far is the methods used to measure turbidity, flow, level, and certain analytical measurements. Also the complexity of the process with which we are dealing.